Okay, so now that we have looked at life on Earth, what we mean by life, how we think it might have gotten started on Earth, a few main points about some of the history of life on Earth and its adaptation to different environments, we can now begin to look beyond the Earth to see where we might look for life elsewhere. And at this point, we have not found life elsewhere beyond the Earth. So Earth life is our only known example. But as we go to move out through the solar system, the question will be, where should we look and where is it most likely that we'll be successful in finding life if it does exist? And what are some other areas where it just really doesn't make any sense to look for life, at least life as we know it? We'll also talk about weird life toward the end of this second section of the course. Life essentially not as we know it. So when we're looking across the solar system and trying to evaluate whether or not specific planetary bodies or areas on those bodies might be habitable, might be environments where living organisms could have originated, evolved, and continued to be there. We essentially evaluate these spaces on the basis of three main criteria. One is there some kind of available energy source within this habitat? Because we know from the first unit how important energy is for driving metabolic processes. Second, are there nutrients that the potential organisms could use in association with that energy to construct these low entropy, highly organized biochemical systems and structures that we know characterize life? And finally, much of our search for life in the solar system has revolved around where can we find liquid water. In general, for life processes to occur, which are essentially complex chemical processes, we need to have some solvent within which those processes could take place. Currently, much of the look for life elsewhere in the solar system is focused on water as being that solvent. But it's not the only game in town, as we'll talk about later. But it is a very good solvent for hosting the kind of reactions that are needed for biological systems. So just to look at these three factors in a little bit more detail, in terms of energy, we know that sunlight is a very important energy source here on the Earth, but there are other energy sources that organisms use as well. Chemical energy, so those chemosynthetic bacteria and other organisms that are living at the bottom of hydrothermal vents on the Earth are able to use those reduced chemical compounds in order to structure their metabolism. It's a big question about other potential energy sources. Are there any organisms that can somehow make use of gravity or tidal energy or radiation? All of these are energy sources that are out in the environment. We know for certain that sunlight and chemosynthetic systems are critical, but there's potential for others. In terms of nutrients, of course, we've been focusing on and will continue to focus on the importance of carbon. Carbon is critical for being able to build up very complex molecules, carbohydrates, amino acids, nucleotides, because of the ability for carbon atoms to bond together in very complex chains of atoms with associated side groups. There are a variety of other important elements that Earth life makes use of. I won't list them all, but clearly, nitrogen and oxygen and hydrogen and phosphorus, sulfur, iron, magnesium, manganese, and all of those minor constituents. So, to what extent does the environment provide a source of these kinds of materials? And then finally, we've talked a little bit about why water is such an important potential solvent. It is liquid over a quite wide range of temperatures, so from 0 degrees centigrade to 100 degrees centigrade. It is a solvent that can dissolve both polar and nonpolar materials. And one other very interesting feature of water is that because of the way ice forms, ice is actually lighter than water, less dense than water. And so when lakes freeze over, for example, on the Earth, we've got the ice going up to the surface. If water didn't have this property, then the ice would accumulate at the bottom of these bodies of water, and it would be very difficult for those bodies to ever really fully thaw during what we might call the growing season. There are other potential sources, though, or potential solvents, including ammonia, various water ammonia mixes, hydrogen peroxide, other kinds of fluids can act as solvents under different temperature ranges. And so if we are able to think beyond water, then we have the potential to look for life beyond what we would think of as the kind of temperature regime we see here on the Earth. Okay, so just a very quick survey of the solar system. We have 4 rocky inner terrestrial planets: Mercury, Venus, Earth, and Mars. These are all essentially rocky planets with some differentiation of core and mantle and crust. Clearly, one thing that differentiates the Earth or makes it stand out is the high prevalence of liquid water on its surface, oceans, clouds, a clear hydrological cycle. We'll look quite extensively at Mars. Mars has probably had the most interest in terms of other areas in the solar system for life. But we will see that attitude might be changing a little bit over time. I'll talk a little bit in the overview a little bit later. Some comments about Venus. Mercury, is very difficult to imagine that there's a booming ecosystem with life on Mercury, given how close it is to the sun. So beyond those terrestrial planets, we have gas and ice giants out in the outer solar system. Of course, this figure is hopelessly not to scale. Jupiter and Saturn are both gas giants with very small-ish cores in the middle. The planets themselves are not really considered to be good candidates for life, but as we'll see, there's a lot of interest developing around the moons that are surrounding Jupiter and Saturn. Uranus and Neptune are ice giants. They don't have quite the same gaseous composition, at least not to the same extent as Jupiter and Saturn. Further out, much colder, and not much interest in most of their moons from an astrobiological perspective. Then we have all of these minor bodies, asteroids in the space between Mars and Jupiter, Kuiper Belt objects, including Pluto, again, minor, smallish worlds, further and further out, colder and colder. And so, really, in terms of looking for life in the solar system, it's going to be a focus on Mars, and there's going to be a focus on the moons of Jupiter and Saturn. Okay, so there's a classical notion of habitable zone in a solar system, also kind of known as the Goldilocks zone. Not too hot, not too cold. And what this figure shows is how that Goldilocks or habitable zone varies with different solar intensities. So one aspect of stars is that the mass of the star has a big influence on the properties of the star. As you go from smaller to larger stars, you get stars that are increasingly hot, increasingly bright, and also increasingly short-lived. So these small red dwarfs burn slowly. Burn is a colloquial term. They're not actually burning anything. It's all thermonuclear reactions. But red dwarfs basically are cooler. They use up their hydrogen fuel more slowly, and therefore they are very long-lived. If you get to look at massive stars, which really aren't shown on this scale, stars can get even bigger than this. The more massive the star is, the faster they burn, the hotter they are, and consequently, the further out away from the star where you would find conditions to have liquid water on the surface of the planet, which is essentially what this habitable zone is describing. So if we're talking about an Earth-sized star, like our sun-sized star, like our sun, we're really talking about this situation here. And clearly we know that Earth is in that Goldilocks zone where it's not too hot, not too cold. We have the ability to maintain liquid water on the surface of the Earth because the temperature is right. Venus is, in this figure, shown outside of the habitable zone, but in some respects it is almost in the habitable zone. But as we'll talk about in a minute, we've had on Venus a runaway greenhouse effect that has really had a big issue with the habitability of the planet. Mars is just on the outer fringes of the habitable zone, so clearly the conditions we'll be dealing with there is that it's much colder than the Earth. The other thing we'll look at is the size of the planets. Mars being so much smaller than the Earth and therefore not maintaining a dense atmosphere that will allow it to also have liquid water on the surface. So Mars is very cold and dry. Venus is a hellhole, hot enough to melt lead on the surface, atmosphere full of sulfuric acid, and no liquid oceans on the planet. Then we have these outer planets, Jupiter, Saturn, Uranus, and Neptune. Notice this is a logarithmic scale, so Saturn here is 10 times as far away from the Sun as the Earth is. Pluto is even further out at 40 times further away from the Sun than the Earth. So again, what we're dealing with out here are planetary surfaces that are way too cold to maintain liquid water, and therefore we need to look for habitable areas not on the surface of worlds out here, but in the subsurface, as we'll look at in a minute. Okay, just quickly, one of the exercises for this week is to send you to this site where you can actually play around with some of the different controlling factors for habitability that we'll be talking about. So This site basically runs off a mathematical simulation of how the intensity of the star that the planet is around, the orbital distance from that star, and other planetary factors like albedo, which is the degree to which the planet reflects light rather than absorbs it, and the greenhouse effect, how all of those work together to determine the overall planetary temperature and whether or not that planet would support liquid water at the surface. So we'll use this site for you to play around with simulating the comparison between Mars and the Earth or Venus and the Earth, or changing the greenhouse effect on the Earth or the albedo, and see how all of those changes affect the habitability of the planet. So again, this gives you a chance to explore the influence of distance of the planet from the sun, greenhouse effect, which has been very important in the case of Venus, as we've talked about, albedo, to what extent the planet reflects rather than absorbs sunlight, how all of these factors together work to influence the average temperature and therefore the habitability of the planet. So it's a good chance for you to play around with some numbers, do some analyses, create some graphs, and show that you're fulfilling that aspect of the natural sciences gen ed requirement. Okay, just a quick word about Venus and why we're not going to spend much time looking at Venus as a source, as a potential habitat for life. In many respects, Venus is quite similar to the Earth. It's much more of a twin of the Earth in many of its characteristics than Mars is. Venus is a similar size. It has a thick atmosphere like the Earth, unlike Mars, which has very little atmosphere. It's slightly closer to the Sun, but presumably, and you can see the comparison of the sizes here. So, in many respects, Earth and Venus early in the solar system probably started out very similar to one another, but their paths, their histories diverged quite radically over the last 4.5 billion years that the solar system has been around. So as opposed to developing into a habitable water world like the Earth, Venus is this sort of hellhole. And what is really known to have happened now pretty securely is that Venus was the, I don't want to say victim, but the conditions on Venus resulted from essentially a runaway greenhouse effect. There are a lot of greenhouse gases that can potentially trap heat on a planet, and you're probably familiar with carbon dioxide because that's the greenhouse gas that we talk about, CO2. But there are other greenhouse gases. Methane is a greenhouse gas that some people are getting increasingly concerned about here on the Earth, but also water vapor is a greenhouse gas. Essentially, any molecule in the atmosphere that has more than two atoms and has the ability to absorb heat by changing how those atoms are stretching and twisting and so forth, have the ability to act as a greenhouse gas. Probably Venus started off with liquid water oceans like the Earth, an atmosphere with carbon dioxide and water vapor, a water cycle that would have been very similar to what was on the Earth. But because Venus was a little bit closer, overall Venus was a little bit warmer, and that increased loading, that increased temperature from the higher amounts of solar radiation, would have resulted in the temperature of Venus being just a little bit hotter. And we know as temperature increases, then that increases the rate at which water evaporates from the oceans. And that water is going to go into as water vapor into the atmosphere. And that water vapor in the atmosphere is going to increase the greenhouse effect, which in turn increase the temperature, which would in turn increase the evaporation of water, which would jack up the greenhouse effect, which would raise the temperature more. And you get this positive feedback loop where essentially these feedback mechanisms run out of control, and eventually all of the water from Venus's oceans would have been up in the atmosphere, leading to a very pronounced greenhouse effect and very much elevated temperatures. And at the point where Venus lost its oceans, it would also no longer have any option for removing carbon dioxide from the atmosphere. So as volcanoes erupt and produce carbon dioxide on the Earth, much of that carbon dioxide is absorbed by the ocean into various minerals, carbonates, and so forth, which gets buried back into the Earth and cycled through the Earth's crust, and then erupted again through volcanic activity. With the loss of oceans on Venus, there would have been no way for Venus to remove or sequester carbon dioxide out of the atmosphere. So with continued volcanic eruptions, there would be not only large amounts of water vapor in the atmosphere, but also large amounts of carbon dioxide, another greenhouse gas, which basically results in the very high temperatures that Venus now experiences. We will, however, talk about moons in the outer solar system, especially moons of Jupiter and Saturn. Because while they may be frozen worlds at their surface, we'll see there are mechanisms for heating up the insides of the planet, and that a number of these worlds, underneath their icy crust, may actually have a subsurface ocean. And of course, where there's an ocean, an energy source, and nutrients, we're interested in whether life could be there. So we'll focus a lot on Europa, which is fairly certain to have a subsurface ocean. Enceladus, one of the moons of Saturn, is kind of a strange case because it is much smaller than some of these large worlds, large moons circling Jupiter and Saturn. But there's also evidence that there's liquid water under its surface. Titan is potentially a candidate for having weird life. Titan has a very dense atmosphere. It has a fluid cycle that's not based on water, but it's based on methane and ethane. And so there's the potential for non-water-based life on Titan, as well as the potential for, again, subsurface oceans of liquid water. So those are the main ones that we will focus on when we get out to the outer solar system and take a look at some of these giant moons of these giant planets. Just one final comment. If you look at them, they're essentially worlds in and of themselves, and some of these are actually as large as Mercury. So if Ganymede, for example, were orbiting the Sun instead of orbiting Jupiter, it potentially could also be considered a planet. There's potential for a subsurface ocean in Ganymede, less of a potential for subsurface ocean in Callisto. And Io is very interesting because it is very volcanically active for reasons that we'll talk about when we get to that section of this part of the course.